Hello, I'm the presenter Chanhyuk Park, and I'm going to introduce a paper called Water Ticket Hypothesis Finding Sparse Trainable Neural Networks, which was accepted at ICLR 2019 and received the Best Paper Award by Franco. So, as you can see, this paper is about network pruning. And what is network pruning? Network pruning is a technique to reduce the parameters of the network which achieve the similar performance compared to the original one. And usually it uses the following methods to prune the network. We first train the network and remove some structure, a node or the weights of the network according to their importance, which can be the magnitude of the weights or magnitude of the gradients. And we fine-tune the pruned network and repeat them until some criterion is met. And I brought some two famous previous works from network pruning. The first one from Han at 2015, and the second one by Lee at 2016. And as you can see in those red boxes, the pruned networks, which have significantly smaller parameters, achieve a similar performance compared to the original one. Even for like VNet, AlexNet, VGG, and even for deep networks for ResNet. So, like, we can think of this is very weird because the pruned network is the subnetwork of the original network. Then, how is this performing better than the original one? The original one always can be the same state as the subnetwork by just setting some weights as 0. So, yeah, how is this happening? The authors tried to catch this phenomenon and proposed a hypothesis called the water ticket hypothesis. Let's say network F reaches minimum validation loss L at iteration J with test accuracy A, and F dash reaches minimum validation loss L dash at iteration J dash with test accuracy A dash. Then the water hypothesis predicts that there exists a mask, which means there exists a pruned network that with smaller iterations it achieves higher performance with significantly smaller parameters. And we call that stuff such F dash, which means the pruned network, as the winning ticket from now on from this presentation. And the authors try to prove them empirically by doing lots of experiments. And I summarized the experiments as the following. They did the experiments on fully connected networks with the MNIST dataset and the famous LENet with various pruned weights, various remaining weights. These numbers show the remaining parameter weights, and there can be a lot of ways to prune them. As I introduced at the beginning, there are lots of ways to prune the network. So they first test which is the best method to find the winning ticket. And after that, they experiment on the convolutional neural network at CFAR10 with various convolutional neural networks like ResNet or VGG. So, first, I'll introduce the method how the authors find those winning tickets. First, it randomly initialized and trained the network, and second, it pruned p% of the network's smallest weight, which is same as creating a mask and masking them as value as 0. And we do it by this layer-wise, meaning that each layer is pruned p%, not the whole network. And the important one is the step 3. We reset each remaining weight to the value from the step 1, which means the initialized value at the first place, and train the network with that initialized value. And we do this step 2 and 3 iteratively. What I mean by step 3 can be summarized in this figure. We first initialize as set type 0, and after training and pruning, the parameters should be changed as theta. But after doing step 2, we change the set type theta 1, which is the initial value, and redo the process again. So with this method, we can find the winning ticket of the fully connected network. This x-axis is the training iterations and the y-axis is the test accuracy, and these numbers show the remaining weights of the parameters. And as you can see, 100%, which is the original one, performs worse than the half pruned and the 21% remaining weights. the pruned network, which is the green and the orange line, is above the blue line, showing that it achieves higher performance and it converges faster than the original one. And as you can see, for the other lower pruning rates, the 3.6 remaining parameters almost matches the performance of the original one. This is really cool, right? And this is the experiment for the method for finding the lottery ticket. And as you can see, there can be lots of ways, but they summarize them in these four. This winning ticket means that we use the step 3. We use the first initialized value and reinitialize them as that value. And the random winit means that we don't use the first step 1's initial value, just reinitialize and randomly keep again. And from this experiment, as you can see at this graph, the x-axis is the percent of the weight remaining, and the y-axis is the early stop iteration. This early stop criterion is the minimum validation loss. So these plotted graphs means that they are the value at the minimum validation loss. And as you can see, as you can see over here, the blue line, which is doing it iteratively, and our winning ticket method, converges faster at all kinds of pruned rates, and yeah, and achieves higher performance because we can see that the blue line is above the orange, red, and green ones. Yeah, so we showed that doing it iteratively and reinitializing with the first step initialized value is good at finding those winning tickets. So from now on, we will fix this method as the finding the winning ticket method and proceed the experiments with those. So the next one I said is the convolutional networks. These conv2, conv4, conv6 means the depth of the convolutional neural networks, and these straight lines are the method used to find the winning ticket, and the dotted lines means that the the step 3, just not using the step 1's initial value, but just reinitializing every time doing the iterations. So as you can see over here, these dotted lines are always above the straight lines. This means that again, this axis is the percent of weight remaining, and the y-axis is the early stop iteration. It means that at all kinds of remaining weights, our network found by our method converges faster than the other methods and performs better because this, at the accuracy, as you can see at the accuracy, the straight graphs are always above the dotted ones. So we can check that we can find the lottery ticket hypothesis. You can find the lottery ticket network in convolutional neural networks. Yeah, and I have to bring this goal pruning concept. We just did it by layer-wise pruning, just pruning the p% of each layer of the network. But now we are pruning the p% of the whole network. We're doing this because if the network gets deep and deep, the layers at the deep layers have much more parameters than the first layer. And if you just prune each those layers p%, it is unfair to the parameters having the small one because the parameter size doesn't match, and the small areas can be the bottleneck when training the network because it has too small parameters. So let's look at the results of the deep convolutional neural networks, which are the VGG and ResNet. They show the similar phenomenon, so I'll just explain the VGG one. As you can see, again, these straight lines are the method using the lottery ticket hypothesis method, and these dotted lines are just randomly initializing at the third step. And as you can see, that these straight lines are again above the dotted lines, meaning that it performs better, and even the remaining weight of the parameters decreases. It does not erode quickly compared to the dotted lines. But the fun part is, even we train with the water ticket hypothesis method, uh, with the learning rate of 0.1, it achieves the same phenomenon as the dotted lines, which means that we didn't find the water ticket network with this method. And this is really weird, and the authors did not explain it clearly. But with the smaller learning rates, we can still find them. And if we use a warm-up, we can still find them too. So yeah, this is some future work to why is this phenomenon happening. But still, we showed that using smaller learning rates or warm-up, we can find the winning ticket. So water ticket hypothesis is not wrong until these experiments. So yeah, to sum up, we showed that the pruning finds winning tickets that learn faster than the original network while reaching higher test accuracy and generalizing better. And this paper proposes the water ticket hypothesis as a new perspective on the composition of neural networks, and they show that the importance of ticket initialization when network pruning, and the structure is always also important when pruning the network. And we see that the winning tickets have improved generalization compared to the original ones. Yeah. So thank you for listening to my presentation, and Minhak will be presenting the next.
Thank you for a nice introduction, Tanya. I'm the presenter Minak Song, and our second review paper is Uniform Convergence May Be Unable to Explain Generalization in Deep Learning, published in NeurIPS 2019. So we will start with the background. Last year, GPT-3 model came out with 175 billion parameters, showing state-of-the-art performance in NLP tasks. In fact, the size of the neural networks are getting larger and larger in the last few years, not only for language models but also in image classification. Bigger models are showing higher generalization performance, and this is actually counterintuitive in classical perspective. Revisiting the classical ML theory, it says that big models should generalize poorly. This is because the standard uniform convergence bound increases as the number of parameters increase. So it fails to explain generalization of heavily overparameterized networks in practice. A classical U-shaped generalization curve we can easily find in ML text also implies that increasing model size will eventually fail generalization. However, in practice, as model size increases, the generalization error eventually decreases, giving this double descent generalization curve. The recent theoretical works are trying to explain this phenomenon by searching the implicit bias of SGD. Using the implicit bias of SGD, they construct algorithm-dependent generalization curve based on uniform convergence, and this tries to make bound decrease as number of parameters increase. These learning threat perspectives use uniform convergence, or in short UC-based generalization bounds. While classical generalization bounds use complexity of the whole hypothesis class, the modern generalization bounds use complexity of relevant subset of hypothesis class, which is essentially considering the implicit bias of SGD. However, these existing bounds are still either grow with number of parameters, or they are small but don't hold on original networks, which means that they are not fully explaining the generalization phenomenon yet. And motivated on this paper steps back and studies the limitations of uniform convergence bound. And their first finding was that they empirically observed that existing generalization bounds grow with the training set size, which is actually unexpected. And their second finding was that they proved the failure of UC-based generalization bounds in a particular setting in deep learning. First, for empirical failure of UC, The experiment setting is quite simple. They used MNIST for classification tasks, minimizing the cross-entropy loss with fully connected ReLU network. The stopping criteria for training was until the 99% of the training data are classified by a margin of at least 10. Here, the margin means that it is the difference between the logic output, the pre-softmix layer of the correct label, and the maximum logic output among other labels, which is not correct. So they classify until they're all classified by margin at least 10, and then they measure the generalization error and existing bounds, varying the training set size. And this left graph shows that a decrease in test error as the training set size increased, and this is actually what we have expected. However, the right graph shows that increasing and existing bounds as the training set size grows, and this means it fails to explain dependence on the training set size. Next, for the provable failure of UC, we first review the essential concepts. First, let's say S be a training set and HS be a hypothesis picked from a hypothesis class H by the given algorithm. Then the generalization error epsilon is a function of M and delta, defined by the smallest epsilon such that the probability that the difference between the test error and the training error is smaller than epsilon is greater than 1 minus delta. Second, the standard uniform convergence bound is defined by the smallest epsilon such that the probability that the largest difference between the test error and the training error among all hypotheses should be greater than 1 minus delta. And the real key concept in the proof of this paper is the tightest uniform convergence bound. This tightest UC bound considers the most refined subset of the hypothesis class H star, which is defined by only the hypothesis picked by the algorithm across different draws of the training set. So this set essentially ignores any hypothesis that is never picked by the algorithm. So using this H star, the tightest uniform convergence bound is defined by the smallest epsilon such that the probability that the hypothesis in H star is difference between the test error and training error smaller than epsilon with probability larger than 1 minus delta. Since this is possibly most refined UC bound, proving the failure of this tightest UC bound will actually imply the failure of every refined UC bound. Using the tightest uniform convergence bound, the outline of the proof is as following. First, consider an algorithm that has zero training loss and a test error less than epsilon. And for each training set S, suppose that there is a bad dataset S prime, such that S prime is completely misclassified by the hypothesis HS. The distribution of S prime is same to the original training set distribution. Then we can prove that the tightest UC bound is greater than 1 minus epsilon, because the empirical error of HS for the dataset S prime is 1, while the test error is epsilon. Therefore, the generalization error is near 0, but the tightest UC bound is near 1, implying the failure of tightest UC bound. In this particular setting, the failure of UC bound is provable. And this is an example that fits this particular setting. We consider the binary classification task on 10-dimensional hypersphere with one hidden layer ReLU network. And the training minimizes the cross-entropy until 99% of the training data are classified correctly by a margin of at least 10. Here, the label is 1 and minus 1 for each radius 1.1 and 1. And this algorithm has zero training error and near zero test error. Now we construct the best dataset as following. Given the training set as prime, every training data point is projected on the inner hypersphere to the outer hypersphere, and vice versa, mating the bad dataset as prime. Then, we can actually observe that the hypothesis trained with S completely misclassify as prime, satisfying the desired condition of bad dataset. This is essentially because the decision boundary learned by us is actually complex in microscopic viewpoint, and this is making generalization bound larger. Therefore, UC-based bound fails in this setting. In summary, UC-based generalization bound increased with the training set size, and thus this cannot explain a crucial aspect of generalization behavior. Moreover, the decision boundaries learned by deep networks can be actually complex in microscopic viewpoint to render any UC bound meaningless, despite they're actually good at generalization. So this is our reference and actually the end of our presentation. So thank you for listening.